Thank you very much indeed there, Amarpreet Singh, and all the panelists there. Really interesting to sort of do a deep dive into how you can attract venture capitalists to invest in your Cardano sort of entrepreneurial venture. I find this very hard to believe, but somehow we have come very, very close to the end of the final day of the Cardano Summit 2024. But we are going out with something of a bang because we have one more very exciting keynote speech to come with a very special guest. Matthew Vaerewyck is a systems engineer for the NASA Goddard Space Flight Center. Now, Matthew's actually set to join us by live link. He'll probably be there. He's going to be discussing his Text-to-Spaceship vision on, and I'm reading this because it's quite technical, on accelerating mission development with AI and emerging technologies. But like all good keynotes, there's a story behind how it came about. And joining me now on stage to talk us through that story is Sandro Knopfel. Now, he is Global Business Development Lead at the Cardano Foundation, and I would love you to join me in welcoming him to the stage.
Hello, I stay here with mixed feelings. Somehow I know now the summit comes to an end slowly, which makes me sad, but I'm super happy to be here as well and actually to share a bit the journey we had with NASA, how this came together and what are the important elements to actually go to the point where we are today and actually introduce the Matthew to you in a little bit. So one of the key elements is actually you. It's the community, it's partnerships. We all know about the tech, I don't have to tell you about that, it's most relevant, but the whole story actually started in Paris in 2023, early 23, where I was speaking at the Women in Tech conference. And then I got introduced to Crystal Johnson, the Deputy Center Director of Innovation and Research and Technology at the Goddard Space Flight Center. And we spoke about blockchain and its use cases. And this then led to a couple of follow-up calls. After about 4 calls I actually had with my friend Mel, she told me, I would like to invite you guys to Orlando to speak at the Power Source Summit. It's a small summit where you actually have a lot of technologists, scientists, economists from various different industries speaking about groundbreaking innovations and the work they are doing. It was incredibly inspiring, speaking and learning about what is happening in medicine, the evolution of AI, and so on. But the most incredible thing was that we were the only ones speaking about blockchain. So we spoke about blockchain, we introduced what are actually the technology advantages of it, and showed some use cases. And by meeting a lot of people actually from NASA, there was one person, which face you're going to see soon, that's Matthew. And Matthew quickly grasped, there is something here. Looking at track and trace, looking at authentication, traceability, I think we need to deep dive. So after actually the presentation, we had a very good conversation. We exchanged a bit information, which then led to a couple of calls where I actually included my dear friend, Michiel Bellen, my tech wizard, as I like to call him. And together then with Matthew, we started to actually work on a POC about which you will hear a bit later on. So it's about inventory management, it's about supply chain, and it is actually a road where we started to build a POC, but the story doesn't end yet here. So this year I was invited to the Women in Tech event again. So I was at the Women in Tech Summit, I spoke, and I met then Mackenzie Listrup, the Center Director of NASA's Goddard Space Flight Center. And speaking with her about blockchain, she also got excited and actually organized a call with her management team, with our CTO, Michiel, and myself in August. After this video call and introduction to blockchain, we got the unique opportunity to actually go on the ground to Washington, DC, to the Goddard Space Flight Center, together with Fred, Michiel, and I, to actually educate a broader audience and drive the idea and collect a lot of inspiring ways how we could work together. So there is a lot ideation session happening. There is a lot of ways we try to see how can we help and introduce blockchain in critical infrastructure. We don't speak about simple processes. Those are highly complex and critical to success. So one of the phrases NASA uses is failure is not an option. Sometimes that applies. And I'm very, very happy now to introduce Matthew, who will give you insights about some of the dynamics within NASA, what they're working on, and how blockchain may help to actually secure some of the processes. Matthew, the stage is all yours on screen, I would say.
All right. Thank you, Sandro. I appreciate it. Hello, everyone. Sorry that I was unable to make the summit in person. Hopefully next year I will plan to be there. I'm going to talk to you a little bit today about the Text-to-Spaceship vision and how NASA is accelerating mission development with AI and emerging technologies. I'm a hardware guy, so this presentation is going to be a little bit more hardware focused and perhaps a bit different than most of the other talks you've seen. I'm going to start off with what we're doing now at Goddard, building these amazing lightweight structures that are enabling science. Share some hot off the presses technical developments in AI power design automation, and emboldened by these successes, move to the ultimate vision of accelerating the design of an entire mission development process, or the Text-to-Spaceship vision. Recently, we have been getting a little bit of press. You may have seen a few of these news articles in the news. NASA's evolved structures radically reduce weight and weighting. Or NASA's new AI-designed parts look like they're from an alien spaceship. Or one of my favorites, language smanguage. NASA's generative AI builds spaceships, or their parts at least. But that kind of gets you thinking, what if we could build those? After all, missions do begin with a text description of what they must do, and after years of development, that eventually puts a satellite on the launch pad. Can we use the stunning advances in AI in the last few years to get that satellite on the pad 5, 10, 15 times faster and have it more capable than ever before? And accelerate our understanding of the universe? I think we can. More as each new AI advance drops, like GPT 1.0 a few weeks ago. This is the Text-to-Spaceship vision. I know it's a big leap, but let's take a few steps along the way. So, as children, we all love science fiction and spent lots of time probably reading books and dreaming about the future and what this spacefaring humanity would have. We have moon bases and we have giant space stations, and everyone has their own space corvettes, and they can jump at light speed to different stars and galaxies and things like that. Well, one of the amazing things about working for NASA is we get to work on some of the hardest problems out there. The International Space Station, for instance, is an absolute wonder, and it's the second brightest object in the night sky besides the moon. But space is hard. It took 25 years to complete, a global workforce of thousands of people, and over $100 billion to build. Now, for context, as amazing as that is, it has the interior volume of roughly a 747. And unfortunately, it sleeps 7. This just doesn't scale to the future that we imagined as children. Well, let's look at one of the applications where evolved structures and generative design has helped. So this is the EXCITE mission. It's a balloon mission. It's a telescope that flies in Antarctica. And the great part about that is once the balloon goes up, the telescope, even if the Earth turns, is able to point and look at stars in one direction. Well, on the back side of this telescope is a tip-tilt assembly. And that assembly needs to be held very stiffly because any shaking of that assembly blurs the image. It gives us bad science or worse science than we could have had. So, as most projects in engineering, that kind of birthed a number of requirements. So I'm sorry about the eye chart, but the key takeaways here are There's a load of about 10 Gs vertical. So the way that these things work is the balloon goes up, and then once it's completed its mission, we cut the balloon, and the payload actually just falls. And then a parachute releases out of the top. Well, that's a pretty big shock to any system. Also, the mode, which is basically the first frequency at which the structure vibrates, needs to be greater than 100 hertz to avoid excitation from a nearby cryocooler. So basically it's humming along, and we don't want that to blur the image. Also, every bit of mass that you take up is, incredibly, incredibly important. So we have a relatively low mass target of about 200 grams. So we were able to, the PI of this project, Ryan McClellan, was able to give this problem to one of the best designers that we have, Drew Jones. He actually laid out the initial James Webb Space Telescope, and it's currently laying out NASA's next big mission, the Habitable Worlds Observatory, which is a mission looking for Earth-like planets near sun-like stars. So like most things with engineers who use flat paper or monitors that are flat or things like that, your first solution is kind of this traditional designed bracket that you would kind of expect, right? I need to bolt something down here, bolt something up here, drill a couple holes in it, good to go. Well, the results were that it was certainly stiff enough, and we definitely knew we could make it, but it was way too heavy. It was, almost 50% too much mass. So did some analysis, went back, came up with a second iteration. At that point, we had hit the mass target, but it wasn't quite stiff enough, and it was actually going to be really hard to manufacture this. So went back to the drawing board, kind of with the constraint that it couldn't just change directions. So trying to improve on this design, we ended up, kind of going the wrong way. So now we're not stiff enough, we're too heavy, and we don't know how we would make it. So we said, okay, let's, at this point, a typical team would reset. So what would that look like? Well, now we're within stiffness and mass constraints, but we have no idea how we would make that. What composites it would be, how you would make all the connections to those feet. So instead, let's think about what this might look like from an evolved structures point of view. First, what we do is we digitally encode the structural requirements into software, following our written Evolved Structures Guide for NASA applications, which I'll actually talk about later. Using the generative design AI, we can evolve optimal designs that meet the requirements using commercial off-the-shelf software adapted for Goddard's needs. The part you're looking at there in the middle is one that was tested a bunch. This is actually the part I'm holding up in my hand right now. Just for a sense of scale, it's about 15 centimeters tall. And about 10 centimeters deep or so. So, we were able to fabricate these parts directly from generative design using digital manufacturing. And using these industrial processes such as automated CNC and additively manufacturing, we were able to get a huge acceleration in going from input requirements to parts. So to wrap up that one example, using Evolved Structures technology, it took 2 engineers, 2 days to get 4 iterations of a design, and it didn't quite meet performance and manufacturing constraints. However, one engineer with AI in 1 hour was able to do more than 100 iterations. The solution was lighter, 3 times stiffer, 10 times stronger, and the software ensures that it can be manufactured. So what does this look like kind of on a grander scale, right? So most of our engineering processes kind of sit here in the middle, right? So our design, at the beginning, we have our requirements, and then a designer kind of creates a CAD model and says, I think this will work. They hand that to an analyst who may be on leave that week or on holiday. They take some time to do some analysis. They say, maybe you need to fix this or change this, pass it back to the designer. They iterate a few times, and then when they're finally satisfied, they give it to someone who makes a drawing. They go back and forth a few times, make sure that's right. Then you hand it to a machinist, and then by that point he's certainly cursing the engineers, saying who came up with this design, and this process can take months and years. The evolved structures process shrinks that entire center section down to hours and days. And what it allows is it allows the engineer to focus on the requirements and getting those requirements right. We actually demonstrated this, as Sandra mentioned, from requirements to parts in hand in less than 48 hours. In the Orlando summit that was mentioned by Sandro, we actually gave a keynote at 10:30. I began working on a design, seen here, at about 1 p.m. By 4 p.m., we had the finalized design. And by 7 p.m., the part had been flown from a manufacturing facility in Minneapolis, St. Paul, to Orlando. This is that piece right here. And for context, this is about 24 centimeters in diameter and was machined in, I want to say, 18 to 19 hours with post-processing and everything like that. So let's go back to our initial example. That part, the bracket I held up earlier, was actually so successful that the PI, or principal investigator, said, hey, can you do our entire optical bench with this technology? And as you can see here in the top right, that bracket kind of became part of the larger optical bench. Here you can see it actually mounted on the payload for the mission. And I'm happy to report that about 3 weeks ago, this mission did go up and fly, and the bracket was successful. So over time, this is but one example, we've actually come up with 63 different applications. So as the demand for this technology became so high, we started to establish a standard input form to capture all the design requirements for each application in the Goddard Evolved Structures checklist. But it wasn't too long after that ChatGPT kind of took the world by storm and got us thinking, how can we go directly from these requirements and ready to fabricate structures in a fully automated way? AI is really good at text. How can we leverage that? Well, we started to think a lot about how we think and try to capture, when we look at a requirement and we start designing something, what is our brain actually doing? And so we were able to then write down this process, which is a publicly released document, and it's called the Evolved Structures Guide for Goddard Space Flight Center Applications. Well, now that you have consolidated all of your ideas and you have text that can be worked out, you could then maybe make a workflow. So utilizing a program called Sonera, we were able, 2 interns in 1 week were able to use this program with only text input, no CAD, no finite element analysis clicks, and actually automate building structure. And thus the text to structure vision was born. But once software is made and once a problem is solved, it can be solved forever. So if we take that software and shrink it down into one block, into one function, text to structure can now fully automate design and analysis for optimized structure. So we could maybe do that bracket that you saw earlier in an automated way that only takes 20 minutes. On the left-hand side, what you see is input for bolt locations and some loading constraints and material selection. And then you get a CAD output along with all of the finite element analysis that we would normally do for flight. Well, what if I change the inputs for that? Well, now I'm looking at a structure that can hold the detector from the NASA StarX mission. Or maybe I'm holding a magnetometer as part of the Hermes payload. Or I can even extend this even further. And here you're looking at the secondary mirror support structure for the Habitable Worlds Observatory. Now, previously we talked about the A15 bracket being about 15 centimeters tall. The structure here, because looking at something on the screen is deceiving, this is actually a 16-meter long boom arm, and it was solved by the exact same software. So here are some of the other applications that we have. What you're seeing on screen is part of the Mars capsule containment and return system. So as we pick up samples off the Martian surface, you have a Mars ascent vehicle that will take it up into space where it meets an orbiting payload or orbiting satellite. And in the top left corner, what you see kind of looks like a alien tennis racket. As the samples came in, this arm would swing in and would actually stop the samples from bouncing back out. This was the only design that would be light enough to be able to be swung, but strong enough to handle the bounce back. No traditionally designed mechanisms would have worked. Along the right-hand side, you see the lid that would close, that would fully contain the samples. And then on the bottom, you see an empty and populated sensor bracket that would actually go inside the holes there. And those are the sensors to see when the samples are coming in, where they are, angles, velocities, things like that. Some other examples we have are in the top left and top right. Right here, you're looking at the Alice optical bench. We have consolidated 10 parts to 1 and reduced the overall mass of that structure from 3.6 kilograms to 615 grams. NASA estimates that a launched kilogram is about $1 million US, and so that saves $3 million in launch costs. The part in the bottom left is another version of the ones you see up top, and to the bottom right, that's actually another bracket in that assembly that we are doing vibrational tests in. For context, this part is about 36 centimeters tall and also was made through CNC. All of the parts I've shown today are subtractive manufacturing, so they are CNC or computer numerical controlled. None of them are 3D printed. But now we have all of these parts. You see me holding up multiple of them. I've told you there's 63 applications. Well, much like we have processes in place for ensuring that humans don't make mistakes when they do design, we have processes in place to ensure, the same processes in place to ensure that we didn't make an error putting things in, or the AI made an error during calculations. So that basically comes down to TLYF, or test like you fly. Well, what does that actually mean? So Sandro and Michiel and Fred were able to come to Goddard, and they were able to see some of our world-class facilities. For instance, like the acoustics test facility. This facility has a maximum sound pressure level of 150 decibels. What we do is we literally play the sound of a rocket launch, and so we're able to capture what happens with all of that noise nearby. So I threw out a number, 150 decibels. For comparison, 120 decibels is when humans start to lose their hearing. 130 decibels is about a jet taking off from 200 feet away. And at 150 decibels, your eardrum would actually rupture to exposure. We don't put anyone in there. It's fine. It's safe. We do it for testing the loads. We also have vibrational test facilities. These are for doing essentially the same thing, but at a different frequency scale. We also have space chambers that are able to replicate the pressures and temperatures of space and able to cycle these things, simulating what it would be like to be in sunlight and in shadow. We also have the large radio frequency interference test chamber, where we're able to play different frequencies and things like that expected to ensure that both communications stay up and that none of our parts or components experience any failures. And lastly, and most impressive in person, is the high-capacity centrifuge. It's a 120-foot diameter arm capable of accelerating about 2,200 kilograms to about 30 Gs, which simulates launch and landing loads back on Earth or on other planets. So with all of these parts, and I've talked about many of them, we're learning to accelerate by designing and building and testing faster. I mentioned earlier that these parts are validated by tests. And indeed, oftentimes one good test is worth 1,000 expert opinions, and sometimes can be cheaper and faster. But I'm not an expert on all of the tests and facilities that you saw. I design things. I'm familiar with the tests, but I don't operate them. Many people touch these parts as they go through acceptance and manufacturing. So this basically comes down to a massive game of who done it. Our existing tracking mechanisms, believe it or not, actually lack comprehensive supply chain transparency. They don't really track real-time custody of components. We know who did a test, but we don't know where it sits or where exactly someone moved it or things like that. We don't have traceability through our manufacturing and testing. We do, it's just not easily decipherable. Imagine if you had 5 people do 5 tests, and then they all put their documents in a repository. There's nothing that links the timelines. You would have to know that each of those tests were completed. It's a lot of additional human overhead and oversight. Additionally, our cross-agency interoperability is limited and relies on paperwork, either print or digital, which could introduce a lot of efficiencies and potential errors. So what would a Goddard-focused part tracking solution look like? Well, a blockchain solution would easily provide real-time custody of who is holding parts and where they are moving. It would create a digital thread from its manufacturing and inception through testing and then ultimate integration into a larger payload. As the system was able to build out, contractors were brought on board or anything like that, other centers and agencies would be able to be integrated, and we'd be able to pass assets to each other along with the auditable trail of tests. A distributed system would provide geographically diverse backups. If there was a failure of, for instance, cooling or power in a building, the entire system wouldn't go down. And it would enforce consistency management, which would provide easier integration through developing AI systems. So we were able to make use of Cardano's flexible metadata and native assets to create a part and subsystem tracking solution. What you see here is kind of an overview of what maybe a manager or systems engineer or a product lead would use. You see maybe all of the products in the middle under their purview or their custody. On the right-hand side, you see maybe the updates of what's going on with different parts and where they're moving and things like that. So it kind of gives you a broad overview. Well, in order to get that overview, you're going to need to be able to look at each part individually. So here we're looking at a demo part of Test Fuse 1, and you could see all of the actions that were done to it. Transferred, tested, we could upload test reports, and that would then make an auditable digital thread through the entire system. As well as with all of this information, perhaps we could use an AI and say, hey, where is this part now? Or what's the part number? Or maybe even cross mission and say, what parts were used or what testing was completed on this part when used in other missions. So now that we've made brackets, we've made structures, we kind of need to expand this, right? One metal bracket isn't going to solve the problem. So we start to look at text to components, text to subsystems. Looking forward to the immediate future, we see a path to automating other types of components, such as optical mounts, flexures, circuit boards, optics, and also selecting existing components from catalogs, which is a huge, huge way that we spend time. There are technologies in various states of maturity, and we are funded to mature them. By combining component automation of various components with AI agents, we can start to design entire systems. For instance, by combining structures, circuit boards, and component selections, we can actually envision automating electronics box design. Or forgetting circuits, perhaps we could take structures with other structures and then and component selection, and we could actually create trusses. This is something that we are actively pursuing in automating truss design. Or let's go for the Holy Grail, and by combining structures, optics, their mounts, flexures, component selections, we're able to envision automating a design of optical systems, such as optical benches like you saw earlier. We actually plan to demonstrate this in the next 6 months to about a year. So now that you can see how we can combine all of these things into different components, the text-to-spaceship vision starts to take hold, accelerating our missions and leading us from science questions to new understandings faster using computational design and AI, leveraging the power of emerging technologies like blockchain to enhance our part tracking and digital thread management. We hope to get there in the next year or so. So with that, thank you very much. And I hope you enjoyed the presentation. On the screen is my LinkedIn and the LinkedIn of the PI. Please reach out to us if you have any questions. We'd love to talk to you. Thank you.